The next work is real-time gesture recognition from data through key pose learning and decision forest from Miranda, Vieira, Martinez, Leviné, Vieira, and Campos. The speaker is Thales Vieira.
Okay, good afternoon. I'm Professor Thales Vieira from Federal University of Alagoas, and I'm going to present you our work real-time gesture recognition from depth data through key poses learning and decision forests that we have developed jointly by UFAL, PUC-Rio, and UFMG. So, our work is about human gesture recognition. This has been a topic that of active research for many years, mainly because it has potentially many applications, like in the area of control, for example, in entertainment application, or for example, in a domestic utility like increasing the volume of your TV. We have applications in monitoring, for example, in detecting suspicious gestures, like a robber. And we have applications in analysis, like, for example, analyzing dance steps or performance of athletes. So, in the current scenario, we have seen a popularization of real-time depth sensors, mainly because of Microsoft Kinect sensor. So now we can start to think that the remote control is in the past. We can maybe start to think about throwing it away and thinking about that what happens in this famous science fiction movie is a reality. This kind of natural user interface. However, this is still a challenging task because one of the main challenges is that a gesture can be performed at different speeds and sequence of poses. One can say that if you perform a gesture in one speed, this is going to be different than a gesture that you perform slower, for example. So, our approach to solve this problem is by key poses learning. So the idea is that a body gesture we can see as poses evolving over time. However, what we do here is that we are actually discretizing this space of body poses and time. So it's easy to see through this picture that one can represent this gesture of turning a page just by the poses in red. This is actually a discretization of the gesture. So what we want here is to perform real-time gesture learning and recognition, and we want something that is ideal for an average inexperienced user so that it can teach the machine what kind of gestures he wants the machine to recognize. So here is an outline of my presentation. And there are many related work with human gesture recognition, which we can mainly categorize in local methods, global methods, and parametric methods. In the local methods, we can see, for example, the work of Lee, that he actually projects a bag of 3D points of local features in a plane, and he tries to recognize gestures. In the global methods, I can talk about, for example, there is a work that is interesting to us that he tries to recognize gestures but using video, 2D video. So here comes the idea of key poses. This is the first work that we know that of our knowledge that talk about using key poses. And finally, there are the parametric methods. In the parametric methods, there is this work from Raptis from 2011. It's a very recent work, where he uses Kinect skeletons and the joint angles of these Kinect skeletons to detect dense gestures, dense steps. And he detects and analyzes these gestures. And this is also an inspiration for our work. Okay, so here's an overview of our work. We have mainly 3 ingredients. We have a pose descriptor that we extract from a Kinect skeleton. We have a key pose learning machine that must be robust and efficiently detects key poses. And we have a gesture learning machine that must efficiently recognize gestures composed of sequences of key poses. So here is how it works. First, a user needs to train the machine, the key pose learning machine, predefined gestures, predefined key poses, so that he must give examples of the key poses in front of Microsoft Kinect. And from these key poses, the descriptors are extracted and inserted in a training set that fits our key pose learning machine. So once the machine knows how to recognize how these poses are, we can begin to recognize key poses. So basically now the user can perform a pose in front of Kinect, and the machine, the key pose learning machine, is able to return the key pose that the user may be doing or not. So now that we can in real time recognize key poses, we can start to think about gestures. So we need to train our gesture learning machine. So what we do is that now a user can perform a gesture in front of the Kinect. Our key pose learning machine can detect the key poses that appears through time. And these key poses, this sequence of key poses, are inserted in a training set. Finally, now the gesture learning machine is able to recognize gestures. So now the user can perform any gesture, and the machine will recognize all the key poses through the time, and these key poses go into a buffer, and the gesture learning machine tries to identify what gesture is that, if he is performing a gesture. Okay, so now I'm going to talk about the pose descriptor. So basically we use skeletons from Kinect Sensor, which is a real-time depth sensing system that streams depth data and skeletons at 30 frames per second. We use a skeleton like this, where we have the torso joints in red, the first degree joints in green, and the second degree joints in blue. So our objective is to design a pose descriptor that concisely represents the relevant pose information. So what we did is that we improved the work of Raptis that uses local spherical coordinates. What he does is that he converts a local Cartesian representation to local spherical angles. Sorry, to spherical angles in a local coordinate system, in a local basis. So for the first degree joints, it's easy to compute these bases. What we do is that we use these 4 torso nodes in red to define these local bases, and then we translate the bases to each joint that is adjacent to a first degree joint. In this case, we translate it to the shoulder that is adjacent to the elbow. And then we just compute the spherical angles. The problem comes on second degree joints. On second degree joints, we want a local representation of the node, in this case, the right hand. So we can't use these local bases like this. That's the way Raptis does. But actually what we did is that we rotate these bases to align the vector U to W. Then we translate and compute the spherical angles. Okay, so the second part is the key pose learning machine. Once we know how to compute these pose descriptors, we are going to use a supervised learning method. What we do is that first we need to predefine the key pose classes that the machine will be able to recognize. And then we must compose the training set. This training set is basically a set of examples of poses represented by the pose descriptors or the local spherical angles and a label that is a key pose class. This training set feeds a machine, a learning machine, and then the user is able to ask the machine, what pose I'm doing? What key pose is this? So the machine we used is a support vector machine. A support vector machine is a binary classifier that basically tries to fit a hyperplane that better separate the data in two classes, -1 or 1, here in red and green. We choose it because it's very efficient for small training sets, and it can also provide nonlinear classification through the use of kernels. So we use a multi-class SVM formulation as we actually have more than two classes. We can have many key pose classes. So we use a one versus all approach where we compute one binary classifier for each key pose, and we use a Gaussian kernel so that this classification can be nonlinear. And then all these classifiers are evaluated for each pose, and the machine returns the classifier that maximizes the evaluation. Observation here is that if all binary classifiers are negative, return negative values, then we don't have any key pose. The user is probably performing a pose that is not any of the trained key poses. It's not from any class. Okay, so now we know how to recognize poses using SVM. Now we can start to think about the idea of representing gestures as sequences of key poses. So here we represent a gesture, as I said, as a sequence of the key poses of where each of these key poses are in that set of predefined key poses. So basically, the user just perform a gesture, and at each frame, we try to identify if the user is performing any key pose, like those in red. And if that happens, for each key pose that is found, it is inserted in our training set. But the problem is that now we want to be able to recognize these gestures, this sequence of key poses, really fast. We need it in real time. So we decided to use a decision forest. So in our decision forest, we formulated that each node will represent a key pose, we will have one tree per key pose, which is the root node. Each path from the root to the leaf represents a gesture, which we store back to front. It's interesting to think why it's better to store back to front than front to back. The thing here is that if we stored front to back, we wouldn't know what's the first key pose of a gesture. And it is interesting to note that two paths may represent the same gesture. We can have one gesture that have, for example, two sequences of key poses. So here we solve the problem that the same gesture can be represented through a different sequences of poses. So here is how it works. The key pose learning machine at any moment returns a recognized key pose. This key pose is inserted in a buffer of the last recognized key poses, and then we query our decision forest that tries to recognize a gesture that is stored in the leaf of the tree. Here is an example to see it more clearly. The key pose K1 was detected, inserted in the buffer. So we go to the tree of key pose K1. Then we keep going in reverse order in the buffer, K2, K3. So we found the gesture G1. But we also wanted to consider time constraints, so that maybe the same sequence of key poses can be actually two gestures if performed at different speeds. So what we do is that actually at the leaf node we can store vectors of time intervals at where the user trained the interval, the times that were trained by the user between the key poses, and then we have this time test that excludes if there is one of the intervals is bigger than a threshold, and if we still have more than one, we return the gesture that minimizes this difference. Actually, this is just the sum of the difference of time intervals. So we return the gesture that was performed in a speed that's more similar to the trained one. So here's the results we prepared. For setup, we designed a set of 18 key poses, which are these ones with these labels. For each key poses, we asked one trainer to give 30 examples of each key pose, which are just small variations of the same key pose, like a drunk man, something like this, just small variations. And we also trained 10 gestures, where this same trainer executed each gesture 10 times, so that we can catch different sequences of key poses representing the same gesture. So here are some results for robustness. We asked the 10 inexperienced individuals to perform the trained key poses 10 times, and we obtained this average recognition rate of 94.84%. It's interesting that this worst individual here was a girl with a big curly hair, so that we couldn't track her skeleton very well. So on the last column, she tied her hair, and so we improved a little bit. Well, we performed some tests of stability of the training set. We performed out-of-sample tests by removing 20% of the training data, computing the SVM classifiers, and we tried to classify the removed training data. The results were very, very satisfactory. with only 4.16% false classifications and 3.45% unclassified key poses. Here's a small video showing the recognition of poses in real time. And we also, similarly, we performed robustness tests for gesture recognition, and we asked 10 inexperienced individuals to perform the same gestures that were trained. And here are the recognition rates that were very good, and some more tricky ones satisfactory. Here's another video showing the gestures being detected in real time. The last gesture, this goodbye gesture, it has a time constraint, so it is only detected after, I think, 2 seconds. The user is with his hand like this. About performance, some performance considerations. Performance is our strength, our bigger strength, because the bottleneck is just a preprocessing one, which is computing the SVM classifiers, which for a training set of 2,000 key poses examples of 18 classes, we needed only 3.9 seconds to compute these ones. And once they are computed, they can be stored, so we don't have to keep recomputing it unless you change your training set. And during training and recognition, we easily achieved a recognition rate of 30 frames per second, which is the limit of the Kinect. And this is mainly due to the low tree depths of our decision forest, which is basically because a gesture is composed only by a small quantity of key poses. For the comparison, we have some trouble because we didn't find many works on that is more for the natural interface problem, but we found works on what I think is a little bit different, which is action recognition. So we use the data set of Lee, which is composed of 20 gestures, where for each gesture, 10 individuals performed each gesture 3 times. So in his experiment, he used 3 subsets of these 20 gestures, and he performed a cross-subject test, where he used just half of the individuals for training and half for recognition. And these were his results on the left column. This is a recent work from Vieira, and this is our method. It's interesting to note that we had a bad result here, and this is mainly because in this subset AS2, there are very delicate gestures like drawing an X, which is very hard for the Kinect to catch the skeleton differences. This is one of our main limitations. We are limited to the quality of skeleton tracking. And this is really an issue for very delicate gesture, like drawing a circle, crossing an X is very hard to differentiate. And also another limitation is that the predefined gesture, the design of key poses, a priori is maybe not the friendliest solution for an average user, for an inexperienced user. And we are currently working on that, maybe an automatic key pose generation. We also are thinking about working on skeleton tracking algorithms, which is another area. We also want to improve the method for the time-constrained gesture recognition, And another detail is that maybe we can improve our method by taking into account the periodicity of the key pose descriptor, as the nature of the angles is periodic. So thank you for your attention, and just for fun, we have linked our method with a media player so that we can control a media player by just in front of the Kinect, just performing gestures like clapping the hands to start or pause the music, increase the volume, passing the music, or returning to the previous song. Just a second. The volume.
Eu devia estar contente porque eu tenho emprego, sou dito cidadão respeitável.
Next song.
Eu sou a mosca
Increase the volume.
Que pousou em sua sopa.
Next song. Next song again. Previous song. Previous song again.
Eu sou a mosca.
And stop. And that's it. Thank you. Any questions?
Questions? Is there any question?
Thank you for the presentation. I like the result that you have presented very much, but I would like to raise your attention to one more limitation, maybe to help to broaden your scope in the near future. That I think there is a limitation for outdoors, because currently I think the Connect does not support outdoors.
Definitely,
so
it must be indoors.
yeah, so maybe you should start looking for maybe other sensors or something.
Yeah, actually, our method starts with a skeleton. We are not even considering what's the sensor or what's the tracking algorithm. We just consider that we have a skeleton like that one, with that nodes, with that joints.
Any other questions?
Hi. Which SDK did you use? What? SDK did you use?
OpenAI. OpenAI.
There are any other questions? So let's thank the speaker again.